Ever wondered about the sun's dynamic dance of solar cycles and magnetic activity? This fiery star at the heart of our solar system is far from static. It undergoes rhythmic cycles of magnetic activity that play a pivotal role in shaping space weather and have far-reaching impacts on our technological infrastructure. Think about the sun as a blazing celestial furnace, constantly in motion, with its magnetic forces choreographing a dance that spans across billions of miles. This dance is not just visually captivating, but it's also scientifically intriguing. It's defined by solar cycles, roughly 11-year periods of increasing and decreasing solar activity, and magnetic activity, an intricate process that happens within the sun's interior and leads to the cyclical variation we observe. This dance, this constant ebb and flow of energy, is what we'll be exploring today. So, let's dive into the solar cycles and magnetic activity, starting with solar cycles and sunspots. Imagine a rhythmic dance that lasts for about 11 years. That's the solar cycle for you. The sun, our solar system's blazing star, is not as constant as it may seem from Earth. It goes through a cycle of activity that peaks and ebbs approximately every 11 years. This periodicity is known as the solar cycle, and it's characterized by the waxing and waning of sunspots on the sun's surface. Now, what are sunspots, you might ask? Well, sunspots are cooler, darker regions on the solar surface, which are teeming with magnetic activity. They are the visual markers of the sun's magnetic field lines getting twisted and poking through the sun's surface. The solar cycle is a testament to the sun's dynamic nature, transitioning between periods of solar maximum and solar minimum. During a solar maximum, sunspots are abundant and the sun's magnetic field is the most distorted. This is when the sun is at its most active, and solar events like flares and coronal mass ejections are more frequent. On the other hand, during a solar minimum, there are fewer sunspots, and the sun's magnetic field is less twisted. This is a period of relative calm, where solar activity is at its lowest. However, even during solar minimum, the sun can still produce noteworthy solar events. It's important to note that while the average length of a solar cycle is 11 years, it can vary. Some cycles have been as short as 9 years, while others have stretched on for 14. Scientists are still working to understand why this variability exists. The solar cycle is not just an interesting celestial phenomenon, it has real-world implications too. The sun's activity influences space weather, which can impact our technological infrastructure. From satellite communications to power grids, understanding the solar cycle is key to predicting and mitigating the potential impacts of solar activity on our technology-dependent society. Now that we understand solar cycles, let's uncover the mystery behind the sun's magnetic activity. What drives the sun's magnetic activity? The answer is the dynamo mechanism. Now, what's this dynamo mechanism? Picture a giant churning engine deep within the sun. It's driven by convective plasma currents, differential rotation, and a complex ballet of magnetic fields. This dynamo mechanism generates the sun's magnetic field, an invisible force that extends far into space. The dynamo also leads to the cyclical variation we observe in solar activity. It's like a cosmic conductor, dictating the rhythm of the solar cycle. When the dynamo is active, it stirs up the sun's magnetic field, leading to periods of increased solar activity known as solar maximum. Conversely, when the dynamo quiets down, we enter a phase of solar minimum, with fewer sunspots and lessened activity. In essence, the dynamo mechanism is the heartbeat of the sun, driving its magnetic pulse and orchestrating the ebb and flow of solar activity. With the dynamo mechanism in action, let's explore how sunspots form and evolve. Sunspots are not just random dark spots on the sun, there's a lot more to their story. Our sun, this colossal glowing ball of gas, is a hub of magnetic activity, and sunspots? They're the visible manifestations of this intense magnetic energy. But how do they form? Picture this. Deep within the sun, magnetic flux lines are twisting and coiling due to the sun's rotation. Occasionally, some of these lines become so twisted that they poke through the sun's surface, creating what we see as sunspots. These sunspots are cooler and less luminous than the surrounding solar surface, which is why they appear dark to us. They're cooler because the strong magnetic field at the sunspot inhibits the convective transport of energy from the sun's interior to its surface. Essentially, the magnetic field acts like a barrier, reducing the amount of heat that reaches the surface of the sunspot. But sunspots are not static. They're born, they evolve, and eventually, they die. In their infancy, sunspots can be as small as our planet Earth. However, over the course of several days, they can grow to be many times larger, even dwarfing our planet in size. During their lifetime, sunspots can merge with other sunspots, creating larger, complex structures. They can also split apart, forming new, smaller sunspots. As the solar cycle progresses, sunspots evolve in a predictable manner. During the solar maximum, when the sun's magnetic activity is at its peak, sunspots are abundant and frequently appear closer to the sun's equator. As we move towards the solar minimum, sunspots become less frequent and tend to form closer to the sun's poles. Finally, after a few weeks, sunspots start to disintegrate. The magnetic fields weaken, and the energy barrier dissipating allows heat to flow back into the sunspot. It gradually brightens and blends back into the solar surface, marking the end of its life cycle. Sunspots can lead to some intense magnetic activities. Let's delve into solar flares and coronal mass ejections. Solar flares and coronal mass ejections are the fireworks of the sun. These dramatic phenomena are born out of intense magnetic activity, particularly in sunspot regions. Let's start with solar flares. They are sudden, powerful releases of energy from the sun's surface, often accompanied by bursts of radiation. Imagine a rubber band being twisted more and more until it suddenly snaps, releasing all the stored energy. That's a solar flare for you, a magnetic snap on a solar scale. Now, on to coronal mass ejections, or CMEs as they are often called. These are colossal expulsions of solar material and magnetic field from the sun into space. Picture a volcanic eruption, but instead of molten lava, it's plasma and magnetic fields being hurled into space at incredible speeds. These solar flares and CMEs, as you might guess, don't just make for a spectacular light show. They have significant effects on space weather, which in turn impacts us here on Earth. They can interfere with our communication systems, disrupt satellites, and even cause power outages. So while these solar fireworks may be millions of miles away, their influence reaches all the way to our doorstep, and that's why understanding them is so crucial. These solar activities are not just spectacular to observe, they are important for us to study and predict. Observing and predicting solar cycles is like forecasting weather, but in space. Just as we monitor atmospheric conditions to predict weather, so too do we observe the sun's activity to anticipate its magnetic cycles. This is accomplished through space observatories like the Solar and Heliospheric Observatory and the Solar Dynamics Observatory. These observatories keep a constant eye on our sun, providing real-time data on its activity. The sunspots, the solar flares, the coronal mass ejections, all these phenomena are scrutinized and recorded. This data is then analyzed, forming the basis of a historical record of solar activity. And just like spotting patterns in weather, scientists use these historical records to discern patterns in the sun's behavior. These patterns yield valuable insights into the timing and intensity of future solar cycles. In essence, understanding the solar cycle is akin to having a weather forecast for space. It allows us to predict periods of high solar activity, which can have significant effects on space weather. This, in turn, impacts communication systems, satellites, and power grids on Earth. Therefore, the importance of understanding and predicting solar cycles cannot be overstated. It is crucial for mitigating potential impacts on our technological infrastructure. So, while we may be millions of miles away from our sun, its rhythmic dance of magnetic activity has profound implications right here on Earth. The sun's activity doesn't just affect space weather, it might also be influencing our Earth's climate. Could the sun be causing climate change on Earth? Let's find out. Current research is probing the possible effects of solar cycles on our planet's climate. Solar irradiance variations and shifts in the sun's magnetic output may subtly alter our climate. Yet it's a complex puzzle involving numerous factors like greenhouse gases, volcanic eruptions, and oceanic currents. Disentangling the sun's influence from this intricate web remains a formidable challenge. The sun's influence extends beyond climate, impacting our technological infrastructure. Our modern world is highly dependent on technology, and solar activity can affect it significantly. Solar flares and coronal mass ejections can induce geomagnetic storms, disrupting satellite operations, causing communication systems to falter, and even threatening power grids. That's why understanding and predicting space weather events is so crucial. It allows us to safeguard our technological infrastructure, mitigating potential impacts. As we can see, the sun's dynamic dance of solar cycles and magnetic activity is not just a celestial spectacle, but a phenomenon with profound implications for our planet and our technological infrastructure.